Hello everyone, welcome to pre-calculus. So on the first day, on the syllabus day, I already mentioned that, I already said that I will be giving you a review on what you already learned in college algebra, because I said that college algebra and pre-calculus kind of very related to each other, very close related to each other. And some of the concepts you learn in college algebra, we're going to be doing that again, but in a deeper way. But in order to succeed in this course, pre-calculus, there's some basic math concept you already learned in college algebra that's require you to memorize, require you to understand. So today I'm going to give you a quick review. I don't know how long it's going to take, but I'm going to review all of the basic concept that I think that in order to succeed in your course, you must be able to grasp and then understand this. Okay, so let's get started. So I'm going to put over here, I'm going to put a review session. Okay. Hopefully, it would take only one session, but I don't know, probably two sessions, two different video, but I try to make it short so that everything will be in one video. And I think the video maybe will be a long one, but just bear with me, okay? So before we start, I just want to ask you, I don't know if you guys remember, what do you guys think? What the most important concept you already learned in college algebra? In college algebra, you learn a lot of things, right? But what is the most important one, you think? What is that? Just take a 1 minute or a couple of seconds, think about what is the most, and kind of ask yourself what you have learned from college algebra. Okay. What did you get after you finish the course? And what is the most important concept, math concept, you remember, or you can recall, and you think that's the most important one in your life, in all the math course you learned so far? Okay, think a little bit. In my opinion, the most important concept you learn in college algebra, it must be function, right? You remember everything you learn, everything you analyze, investigate, everything related to function. Yes, and there are so many type of function, right? I'm going to say not really so many type, but around like 7 or 8 different type of function. And back in that day, we call that parents function. So let's go back and review function. And I put the first Roman function. What is function? What is function? According to our definition, we said, I don't know if some of you already took my college algebra course, and I mentioned this. A function is kind of a relation between two sets, right? Between two sets. The first set we call that input set, and the second set is the output set. But that relation must follow a certain pattern. And what is the pattern? The pattern say that if you have one input, okay, then you will be obtaining only the unit output. Every input, put it into the function, you obtain a unique output, right? Because if you have two different outputs, then it's not the function anymore, right? We're going to talk about that later, but that is the definition of function. Okay, and we learn several types of function. The first type of function we learn, I don't know you guys remember, it is the linear function, right? Linear function, and a very basic linear function in the pre-calculus textbook, we call that the identity function. It sounds very kind of very strange to you, right? Because maybe some of you is the first time you heard that term, identity function. But identity function is really just nothing but just fx equal x. Fx equal. Remember, when you first time you learn the linear function, you know the fx equal to mx plus b, right? And just think about it. If b equals 0 and equal 1, if b equals 0 and equal 1, then you have fx equal x, which is identity function. It's identity function. And the graph of identity function is something like this. Okay. So just if you can graph it by plugging the point, or you can use the rise over run method, or whatever it is. So the line, the identity function, is represented by a line. Okay, and this line makes a 45 degree with the x-axis. Okay, okay. And another, another function I already mentioned, it's called a linear function, y equal to mx plus b. Okay, or fx equal to mx plus b. It's the same thing, right? And b equal what? B equal the y-intercept value. Y-intercept value. Excuse me. And m equal what? M equal slope, right? And everybody must remember what the slope formula look like. Y2 minus y1 equal to over x2 minus x1. Right? Everybody know that given 2 1, you can find the slope easily. Or given the graph, you can find the slope by rise over 1 method, right? Okay, rise over 1 method. Yeah. So that is the linear function, and linear function is represented by a line. It could be any line, as long as it's a line. It could be horizontal line, could be vertical line, it could be any line. Okay, as long as the line is the linear function. And the graph of linear function, I just grab one of them. Okay, something like this. There you go. It's linear function. So let's now get back to identity function. Identity function is nothing but linear function because it's represented by a line, right? And the value over here and over here, okay, this value here we call the y-intercept value. It's nothing but it's the intersection between the line and the y-axis, and the value here we call the x-intercept value. It's an intersection between the line and the x-axis. Okay. Then after you learn linear function, we're going to talk about another concept for the domain of function. But let me finish going through all type of function first. Another function we learn is a quadratic function. Quadratic function. I have a cat and it's keeps screaming crazily. Hopefully it's not in the box. Quadratic function. What is quadratic function? Quadratic function represented by parabola. Remember the parabola, and the parabola could be open up or up and down. And a quadratic function will be can be written in two forms. The first form is standard form, ax squared plus bx equals c. Right? All right. Can you just wait a minute? Let me ask my mom to cover the box because the cat is still screaming. Mom lấy cái gì á, mom gãy cái thùng với con mèo nó nhảy ra. I'm sorry. Okay. So the first type of the first form of quadratic function is a standard form. Okay. So this is standard form. Okay. I would call the leading coefficient. Okay, see it is also for the last coefficient or just a constant term right here. And from this form we can find a vertex. Okay, Or we have another form, we call the vertex form, right? The vertex form goes like this: ax minus h squared plus k, right? With vertex, so this is vertex form. The vertex is h and k, and the vertex can be the x component, which is k, which is h of the vertex, can be found by using the problem negative b over 2a, right? With b is the second coefficient, and a is the leading coefficient of the quadratic function standard form. All right. And the a value is very important. The a value will tell you if the parabola is open up or open down. If the a is positive, we know that the parabola will be something like this, right? And if a is negative, the parabola is going down like this, right? Hopefully you guys still remember. To those who finished the college algebra last semester, and everything should be okay, everything is still in your mind. But some of you, like you took college algebra like a whole year ago, then probably many of you forgot. Okay, so that is quadratic function. Now let's look at another type of function, number 4. What function we already learned in college algebra? A cubic function, right? Cubic function. We learn a polynomial function. Okay, polynomial function is the one that we will take a look at that again in a deeper way in this course in pre-calculus. Okay, and a polynomial function. One of the example of polynomial function I mentioned in the college algebra, which is fx equal to x to the third power, or fx equal to ax squared plus bx plus c. Some of you will wondering like why quadratic function is polynomial function. It is. Quadratic function is another typical example of polynomial function. Okay. And quadratic function, we have a graph that's something like this. Okay, something like that. So this is a quadratic function. This is a cubic function. All right. Or maybe something like this, or negative x to the third power. Okay, that's polynomial function, cubic function. So we call this cubic function. What else? What are we on? Number 5. Number 4. The fifth function. Number 5. The fifth function where they learn in college algebra, it must be absolute function. Absolute function. Absolute, you know, we talk about absolute function, we think about absolute value, right? And the absolute function, they have a V-shaped form. Okay, and the very basic absolute function we already learned is fx equal to absolute of x, and the graph of that is something like this, right? So it is 45 degree here, 45 degree here. Okay. Right, then we learn the vertex form of absolute function. We have something like fx equal to ax minus h plus k, right? Which h and k is the vertex of the absolute function. This one. So if you look at this one, fx equal to x absolute of x, then the vertex is 0 and 0 because h and k 0. Just think about it, h and k 0 and a equal 1, and it give you this, right? All right. Then the a value here, it tell you how slanted the V shape. How slanted the V shape is. V shape is. Okay, because if V is greater than 1, then probably you can say something like this. elongated, you know, and if a between 0 and 1, so this is kind of open up more. Okay, it's kind of something like that. All right, and the vertex for that, and it could be anywhere. It could be here. It could be anywhere. All right, it depends on its integral. So for example, it could be something like that. Okay, and it could be upside down also. If A is turned out to be positive, it open up, and if A is negative, so in this case A is positive, and if A is negative, you will see the upside down V-shaped graph. Okay, so that is absolute function. All right, what else we already learned in college algebra? Anyone remember? Any other function? As far as remember, we have another function we call a rational function. Oh my God, we have 6 functions right now. There's so many things you need to memorize. Huh? Okay, rational function, and we mentioned one about two in basic rational function is fx equal to 1 over x and fx equal to 1 over x squared. Okay, both of them are rational functions because in rational form, right? In fractional form. Well, not all fractional form is rational function, but you see, if you had a polynomial on the top, at the bottom of the fraction, then that is called rational function. And the graph of rational function of 1 over x is something like this. Let me see. Something like this. Okay. With y as a vertical asymptote, and for this one is something like this. It's y also vertical asymptote. But for the top one, we also have horizontal asymptote. So when you learn a rational function, we learn so many things like rational function. We learn vertical asymptote, horizontal asymptote, and if some of you learn if your professor went through slanted asymptote, how to get slanted asymptote, also that I do in the division, remember? Okay. Okay. So that is rational function. The very basic one of rational function. Okay. Number 7. Can you remember what number 7 function? What is the 7th function we already learned? It must be what? It must be the radical function. Let's remember. Radical function. Well, radical function, when I say radical, it's a very general term, you know, because in college we take a look at the square root function only. But when I mention radical function, it could be any root, it could be n root, third root, fourth root, fifth root. But you know, the basic one we learn is the square root 1, or square root of x, and the graph of the square root of x is something like this, right? Something like that. Okay, and maybe some of you who's professor had gone through f of x equal to cube root of x. We're going to have something like that, right? Okay. And sometimes we have n root of x. You know, if some of you took college algebra with me, you know, maybe some of you know, so n root of x, or n could be even or odd, and if it's even, it would be in this shape, and if it's odd, it would be in the second shape. Okay, that's radical function. Number 8. What else? What else have we learned? I don't know if I missed anything. We got absolute, radical function, rational function. Oh, another very important function, I believe. So, it's a piecewise function. I remember when we went through this, a lot of students have trouble with graphing a piecewise function. Okay, piecewise function is what? It's just a combination of more than one function. For example, I call fx over here is the combination of two functions f1x and f2x, or maybe f3x, f4x. It could be more than 2, okay, more than 1, and fx is restricted by a certain domain. So I call domain number 1 here, okay, and f2x received by domain number 2. Okay, so based on the domain 1 and domain 2, in general we call the restriction, we can grab a piecewise function easily. Okay, and its sub-function here, f1x and f1 f2x, we call the sub-function. Okay, its sub-function here could be any type of a function. It could be radical function, could be rational function, anything. Okay, so let's say piecewise function is nothing but it's combination of more than one function. All right. All right. And the D1 and D2 we call what we call the subdomain. You have a college bear with me. I mentioned this term a lot, not really a lot, but when you study piecewise function. Okay. So you see that over here I mentioned the term restriction and domain. Domain. I mean that term we heard so many times, right? It's about to give you the function. The professor give you a function and ask you to find the domain of that function, and you learn how to write it in interval notation. Okay, but actually, what is domain? You want to remember what its domain is? Okay, what is domain? That is one of the aspects of the function we need to look at. We need to take a look. Okay, so on the second part, I want to review what domain and range. It's very short, very easy. Domain is nothing but all the input, okay, that make function define. Okay, it's the set of the input that make the function define. It could be interval. We got interval instead. Okay. So all the value, you can say like that, make the function define. What does it mean by make the function define? It means that when you plug into the function that value, the input you plug into the function, you can evaluate the output. You can get the output. Okay. If you cannot get the output, then it's not. Then that value does not belong to the domain. For example, if you look at the function y, f of x is equal to 1 over x. The value that is not inside the domain, it must be 0, because if you plug in here 1 divided by 0, it doesn't work, right? Undefined. We want it to be defined. If something that undefined, make it undefined, then does not belong to the domain. Okay, so basically that the domain is. Okay. And the domain can be written in interval notation form. Okay, right. Especially when you have a bunch of values. If you have 2 or 3 values, then it will be easy. You just say, okay, the domain of this function is 1, 2, 3, -5, 6. Well, or maybe your professor asks you to find 5 values of the input, 5 input value that belongs to the domain. You know, I usually ask students to do so. Okay, so that is domain and range. After you understand what a domain and range already, you learn about one of the not very important aspect of function. We call it transformation. Okay. Transformation. Hold on, just want to make sure that okay. What is transformation? Transformation is like we transform a function, but why we have to do so? Just think about it. Give you the graph, and I want to investigate. I want to understand more about that function. Okay, the transformation concept will help us to do so. Okay, I want to investigate the domain of that function. Maybe the transformation concept will help us to do so. Okay, when you can grab a function by using the transformation concept and the parent and its parent function, we can investigate what that function look like, and we can investigate the domain of that function easily. Okay, and there's several types of transformation concept. The first one is horizontal, right? Horizontal shifting. Okay, something with what? Something with f of x plus or minus an a value, right? And we have a vertical shifting. We have f of x plus or minus outside parenthesis a value. If add to a value, then move it up, and minus move it down. For this one, the same thing. If you minus, oh, be careful with this minus a, move it to the right, and plus a, move it to the left. Other than horizontal and vertical shifting, we also have something okay. We have another type of transformation. We call that reflection. Reflection. Okay, and the reflection could be a reflection over the x-axis, it could be a reflection over the y-axis, and if it's a reflection over the x-axis, we will have something with f negative y equal negative fx, and if reflection over the y-axis, we will have a y equal to f of negative. Okay, so that is the reflection, and the last one we call the last transformation. We call that vertical stretching and shrinking. So sometimes my handwriting is really bad too. I want to go fast. There's so many things we have to cover in this course. So all the concepts I reviewed you today, you must remember. You have to grasp in order to succeed in order to understand any other concept in pre-calculus. Okay, vertical stretching and shrinking. But how do we know that? We look at a leading coefficient. If y equal to a f of x, and if a is greater than 1, a is greater than 1, then we know that the function will be elongating, so it will be stretching vertically. Okay, and in between 0 and 1 will be shrinking, or sometimes we call compression, shrinking vertically. Okay. And when it's shrinking vertically, it looks like it's in most of the graph will be kind of open up, right? It's kind of like that, you know, or for stretching vertically, it's kind of like this, right? All right. So that is the transformation concept we already learned in college algebra. The sum of the graph is not symmetric about y, nor is it about x. It's symmetric about the origin. Okay. If the graph of that function is symmetric about the origin, we have a specific name for that. We call that odd function. We call it odd function. All right. So on the fourth moment, I want to take a look at even and odd function. Even and odd function. What is even function and what is odd function? Okay, and we have an algebraic way in order to check its even and odd function easily. Well, we have a graphical way also, but sometimes if the function is very complicated, it's very hard for you to check an even and odd function. But you can use the algebraic way to check the function is even or odd. And the algebraic way is if f of negative x equal to f of x, then we know it's even function. And if f of negative x equal to negative f of x, then we know that's odd function. And odd function is a symmetric about origin. And for this one, for even function, is symmetric about y-axis. Okay, I can give you a quick example of what odd function is. The odd function could be cubic function. Right? Just think about a cubic function. One point on the top range, and there's another point on the bottom range. It could be symmetric about the origin. And the example of even function about the y-axis, symmetric about the y-axis is a quadratic function, right? Just think about a quadratic function, right? At the center of the origin is opened up like that, and that y-axis is divide that parabola into half. Okay, so this is symmetric about the y-axis. All right. I think when I talk about function, I think I'm kind of miss going through the domain, you know, thing, because on the second domain, when I talk about domain and range, right, I forgot going through the domain and range of each type of function I already mentioned on the first Roman. So let's go through, go back here and talk about the domain and range of identity function. The domain of identity function must be negative infinity to positive infinity, right? And the range will be the same thing also. Okay. For linear function, everything will be the same, negative infinity to positive infinity. But quadratic function, you have to be careful. The domain will be the domain is also from negative infinity to positive infinity, but the range will be a little bit different. So the range depends on the vertex value. Okay, it could be from the vertex value to positive. Vertex value to, I'm going to put v value to positive infinity, or it could be negative infinity to that vertex value. So it depends on the vertex value over here when we talk about the range. Okay, a polynomial function is very easy. Domain will be negative infinity to positive infinity, and the range also negative infinity to positive infinity. For the absolute function, the domain will be negative infinity to positive infinity, and the range, again, it depends on the vertex value. Okay. Okay. Number 6. The domain will be negative infinity to 0, union with 0 positive infinity, right? Because we have the vertical asymptote over here, and the same will be the same, negative infinity to 0 to positive infinity, because we also have horizontal asymptote over here. But if you look at this one, the domain will be negative infinity to 0, union 0 to positive infinity, but the range is a little bit different, right? The range is start from 0, not included to positive infinity, because you see we have horizontal asymptote over there. Everything the 0 value is not included in the range, or no, the domain. For the radical function, the domain over here will be is included, but it's 0. We can take square root of 0, square root of 0, 0, so 0 to positive infinity included, and the range also 0 to positive infinity. For this one, domain will be negative infinity to positive infinity. The range also negative infinity to positive infinity, because just think about that. For the cube root, you can take cube root negative value also. Okay, but square root, you can, right? You can take square root of -3. It doesn't work if you imaginary number, right? Okay. For the piecewise function, the domain will be the combination. Okay, so the domain will be the domain 1 union with the domain 2. Okay, and the range, you have to look at the graph in order to get the range of the piecewise function. All right, so that is about the domain and the range. So last time we we talked about even and odd function, right? Okay, so I can say that even and odd function is like a transformation, in my opinion. You can use the transformation concept in order to check if the even and odd function. All right, and after we learn even and odd function, we want to add, because when I talk about piecewise function, remember it's nothing but a combination of more than one function. So now what if I want to combine function to another function by using an arithmetic operation we already learned? Okay, how are we gonna do that? So on the fifth problem, I talk about a combination function and composition. Combination of function. It means I want to add, subtract, and multiply by y. So if I have f of x plus g of x, you add two functions together, then they give you f of x. Then we give you f plus g of x, right? And you want the same for subtraction. Okay. If I have f of x times g of x, then we will have f times g, right? Okay, and you do the same for division also. That is when you combine functions together. Basically, you just add them together or subtract them together. Okay. The domain of the domain of the combination of function will be the domain of the new function after you combine. Okay. How about composition of function? What does it mean by composition of function? I want to compose one function to another function in order to get another function. And the notation is used for composition concept is f composed to g. This is mean compose. Okay, and it can be written as f of g of x. Okay, so this is mean what? It means I compose f to g. Compose f to g. It means what? It means I plug g into it. F compose to g. Okay, it means g is plugged into it. Okay, and two functions can be composed to each other to itself. For example, I can compose f to f, I can compose g to g, or all three functions can be composed together. F to g to k, for example. Okay, and the domain of that composition of function will be the domain after you compose, right? So that is composition of function. Another way, let me see if I missed anything else. Because you see, when we just talk about function, there's so many things already, right? There's so many things, a lot. Okay. Now, so even in our function, we know that it could be symmetric about the origin or symmetric about the y-axis. Okay. It's two function. It can be symmetric about another line. It can be symmetric about another line. It can be symmetric about the line y equal x. And if it's symmetric about a line equal x, then those two functions are inverse of each other. So on number 6, I want to talk about inverse. And the inverse function is can be notated as f of negative x. Okay. Back in the day, we learned what? We learned y equal to fx, right? Then we can, after we learn inverse function, we can write it as f of negative y equal x. Okay. And we can use the horizontal line test to check if that function is inverse, it has inverse or not, or is it one-to-one function or not. Okay. Because only one-to-one function then we can find inverse. Okay. If it's not one-to-one function, we cannot find inverse. All right. All right. For example, the line, the graph, the function y equal to x squared is not one-to-one function, and that's why we cannot find the inverse function of fx equal to x squared, a parabola. Okay, maybe some of you ask me what inverse, what is one-to-one function? One-to-one function is the one-to-one function definition is that if you have two different output, okay, if you have two different input, I'm sorry, okay, then their output will be also different. So that is the definition of one-to-one. One-to-one. Okay. If x1 different from x2, then this implies fx1 must be different of fx2. Now just think about it. You look at a graph of parabola, right? You pick one point on the left range, the x point value, -2, and okay, you put 2, right? And you calculate the, you evaluate the output of x of -2 and 2. You see that when you plug into y equal x squared, it turned out to be the same output. It's turned out to be 4. So it's the same. It's not different. And because it's not different, then we know that x squared is not one-to-one. And it is not one-to-one, then we cannot find the inverse of the function fx equal to x squared. Okay. And another way to check the function inverse, two functions inverse of each other or not. For example, given two functions f and g, okay, and I want to see if it is the inverse of each other. We're gonna do the composition. We're gonna compose f to g, okay, and we're gonna compose g to f, okay. And when we compose f to g, it turned out to be x, and this also turned out to be f. Then we can imply that f and g are inverse of each other. Actually, this method is based on the concept that given an f function, okay, in order to check that, in order to check the inverse or not, we can compose the f of -1 to f and f to -1. If it turns out to be x, they are one-to-one function. Then they are one-to-one. Okay. All right. And another important thing I want you to remember is that if they're inverse of each other, then they should be symmetric about the line y equal x. For example, I have a line y equal x like this. Okay, and I have something like this. Okay, I have something like this. Okay, and I said this is fx, and I also have something like this at the bottom here, and I call gx. You see that they're symmetric about this one. Then this, and then in this case, f and g are inverse of each other. Okay. All right. What else? What else we want to review? Let's see what else. Hopefully everybody know how to find inverse of the function, right? I don't want to go through another example. Please look at and you can find an example online easily. But I mean, those concepts is very important. It's require you to know it. Okay. So maybe when you learn a new type of function in this course, then as you to find the inverse, you know how to find the inverse. You just swap x and y, you interchange x and y, and you show y in terms of you show x in terms of y, and then you put it back into x. You flip x and y again, and it gives you the inverse function. Okay. All right. All right. I think the last concept I think is important for you to remember. It is number 4. This is number 7. Roman is monoticity. Okay. When I talk about monoticity of the function, when I talk about increasing and decreasing of that function. Okay. And what is increasing function? I don't know if I spell this word wrong or not. I'm going to check it really quick later. Increasing function. Okay. What is increasing function? It's certain, but think about it. If you have two input value, x1 and x2. If you have x1 less than x2, and this is imply fx1 also less than fx2, then we have an increasing value. Okay, for decreasing value, we have the other way. If x1 greater than x2 and fx1 is greater than fx2, then we have decreasing value. Okay, and when you learn increasing and decreasing value, we also learn something called absolute max, right, and local max. Okay, and absolute max is what? Absolute, which is the highest point in the graph. The absolute mean is the lowest point of the graph. But the difference between the local and the absolute is that for the local one, okay, for the local one, you try to find the hill or the bottom of the valley. Okay, for the absolute one, it could be also, but sometimes it doesn't have to be a hill. For example, for local max, you will see something like this. Okay, so this is local max and absolute max at the same time. Okay, but for local mean, we have something like this, right? So this is local mean, and this is absolute mean at the same time because this is the lowest one. This is also local mean. So this is local mean and absolute mean at the same time. Oh, I'm sorry. Oh, absolute mean and absolute mean and local mean at the same time, because this is the lowest point, but this is not the lowest point. So that's why local mean only. Okay, so in this case it's the local max, but it's not an absolute max if I put it like this. So the this is local max, so this is absolute max because it's the highest point. Okay, so remember, for local max or mean, if you go up, then it must be down, and if you go down, then it must be up. Okay, but for the absolute, it doesn't have to be that way. Okay, monotonicity. I think I spelled this is wrong over here. I'm gonna check really quick. I think I spelled it wrong. Let me see. Monotonicity. Yeah, I spelled it wrong. This is monotonicity. Okay, monotonicity of the function. All right, so I think that is basically that's all concept required to succeed in pre-calculus. Okay, I mean, I don't think that my review is cover everything, but I think it's cover 90% of the concept already. I mean, it's especially unless you know, except for some example, you must practice a lot in order to memorize. But other than that, I think that is the old concept required to prepare for pre-calculus. So please go ahead, watch this video carefully, and let me know if you don't understand any concept here. I will try to give you some example based on this concept, or maybe create an assignment, and that assignment we have some question based on this concept for you to review, for you to remember. But I'm thinking about that. Okay. So we might have some assignment very soon, right? So again, that's all for the video today. So the first video, I don't know how long it will take, maybe more than an hour, but I think that's good enough already. So go ahead, watch the video again if you don't get it, and try to go back to the book, college algebra book, or just try to practice on some example. Then on the next video, we're gonna start with a new topic of pre-calculus. Actually, it's not really new, but you already learned that. But we look into that in a deeper way. Okay, I'll see you next time. Bye bye.